Okay. So last class we started looking at the cross-coupled oscillator. So let's quickly review this. So we said that the equivalent circuit of the frequency selective network in the feedback path, the simplest form of that is just a parallel RLC tank. Okay, and we know that any non-ideal inductor and non-ideal capacitor in shunt can be represented using a narrow band equivalent circuit, which is an RLC in parallel. Okay, now this means that there is a different way of looking at this particular oscillator. Instead of looking at a feedback view, we look at what is called the one-port view of the oscillator. In the earlier case, we were looking at what is called the two-port view because you had the input port and the output port. You are feeding back part of the output signal through a frequency selective network to the input. In this particular case, what we are doing is we only have one single port here, set of ports, and what we are doing is we are connecting both the active circuit and the RLC tank to the same set of two differential nodes. Okay, and what do we know? Let us say the input resistance of the tank was Rp, representing the losses in the tank, and if the active circuit produces a negative resistance minus Ra, it has to produce a negative resistance minus Ra for the circuit to oscillate. Okay, and for stable oscillations, we know that Ra should be equal to Rp. Okay, and we know that before you reach stable oscillations, the circuit needs to start up, and in that condition, your loop gain or your negative resistance needs your loop gain needs to be larger than 1, or the magnitude of the negative resistance Ra needs to be smaller than the magnitude of Rp for it to be more dominant. Okay, and we started looking at the different kinds of oscillators possible. So we started off with the single stage common source with an RLC load, and we took the output and connected it back to its input. We know that the total phase shift is 180 degrees at the resonant frequency, but this is obviously not enough, right? For oscillations we need a 360 degree phase shift from output to input for the output to feedback in phase with the input. Okay, so next thing to do was to take two of these stages and connect them in a loop. Okay, so we took two common source amplifiers with RLC loads, both are identical, and we connected them in this fashion, and we said that the overall phase shift around the loop was exactly 360 degrees at the resonant frequency, because each MOSFET gives you 180 degree phase shift. Okay, and at the resonant frequency you have a 360 degree phase shift around the loop, so the circuit can potentially oscillate. How do you make sure that the oscillation starts up? You have to make sure that the loop gain around the loop is greater than or equal to 1, preferably greater than 1, and the condition, the loop gain around the loop is GMR whole squared. Okay, it is just the gain of this guy multiplied by the gain of this guy, and so GMR whole squared should be greater than or equal to 1 at omega not equal to 1 over root LC. Okay, now we redrew the circuit in a slightly different manner because of the fact that each stage has 180 degree phase shift. You can look at this circuit as a differential circuit because it's completely symmetric on either side, and V1 is 180 degree out of phase with V2. Okay, and this cross coupling clearly shows the positive feedback at work, right, to give you the negative resistance. And we clearly said that the overall negative resistance from this cross coupled pair is minus 2 over GM. Okay, and we came up with the same condition. The condition for stable oscillations or the condition for startup is exactly the same as before. Okay, except that you have Rp equals 2R. That is the only thing to remember. Then we decided to analyze this particular oscillator to see what the output amplitude would be. Okay, because we have ensured that it's an oscillator, we found out the condition for oscillations. Actually, before we do that, let us say we take this particular oscillator. Right? Let me get rid of these highlighting. Okay. Let us say we take this oscillator. Yeah, this is fine. Let us say I take these two MOSFETs, I apply the required amount of feedback or negative resistance, I connect them up in this manner. Will the circuit oscillate? The Barkhausen criteria are necessary but not sufficient conditions. Correct? Suppose I take the circuit and connect it up in this way such that all the loop gain criteria are satisfied. Will the circuit really oscillate? Why or why not? Prathamesh? Why? That was the case for a single LC. That was the case for a single LC. In this case, the capacitor may not need to be charged, but you're getting close to the answer. What is that? Suppose the components have no noise. Let us take that case first. Now you are getting warmer, so let us look at the case when you don't have any noise at all. Will the circuit oscillate? The circuit is perfectly symmetric, right? When you have a perfectly symmetric circuit with no input, there are many stable conditions, right? If you don't give any other input at all and it's perfectly symmetric, the stable condition will probably be the DC operating point, right? I'll have IT by 2 in each half and nothing else, right? The two outputs will be only DC voltages, probably VDD, maybe VDD minus some drop across the inductor, right? But that is pretty much it. I will not see anything else because the circuit is perfectly symmetric. Correct? To get the circuit to oscillate, so in other words, to get the positive feedback to actually have effect and start up the oscillation, I need to provide some kind of asymmetry between the two halves. Otherwise, the circuit will remain at this metastable point that it's at. Okay? Is that understood? Does that make sense? Okay. Now, the asymmetry which is available between these 2 points, there are many different kinds of asymmetries. Okay. Obviously, if it was just mismatches between the components, that may or may not be enough to start oscillations. The reason for that is the mismatch. Let us say you have a mismatch between the transistors. All that means is that the DC operating point may be slightly different. Correct? The DC operating point, maybe the current does not divide exactly IT by 2, IT by 2. It's a possibility. However, what we know is they are both completely identical, but there is an initial charge across one of the capacitors. Okay? Then that initial charge will try to, or will not try to, will actually create a mismatch between these two nodes. Okay? Mismatch in voltage between these two nodes, and therefore it basically turns on one guy and turns off one guy, or vice versa. As long as you create a slight mismatch, it will move over to that metastable point and try to go to the other side. The other kind of mismatch which is available is noise. Okay? There will always be noise from each of these two, M1 and M2, okay, creating small mismatches between the two sides. Okay? It's either noise from M1, M2 or noise from the LC tank. Now, obviously the noise created mismatches will be extremely small, and they will actually start up the circuit when the loop gain is very large. Okay, if the loop gain wasn't large enough, you may not see it oscillating at all. Okay, but in any real oscillator, what do you think will happen? Let us say I'm actually designing this oscillator, taping it out, and I have it on an IC. How do you actually get it to oscillate? There are actually many different ways, right? For example, even turning on the supply of this oscillator could give you enough of a jerk and enough of a difference between the two nodes to actually get the circuit oscillating. Okay, in reality, most of these oscillators which you measure in the lab, that's what will happen. Okay, you turn on the power supply, and there will always be small mismatches between M1 and M2, and that jerk will be enough to not allow the circuit to settle down at its metastable point. Okay, in any real oscillator, that is what will happen. Okay, so now we looked at all the startup conditions. The next step was to actually look at what the amplitude will look like, and to do that we actually tried to create a large signal model equivalent circuit of the cross coupled pair, because at the end of the day the cross coupled pair is modulating the bias current somehow and pumping it into the RLC tank, right? You figure out what that current is and multiply it by the impedance of the RLC tank, you will get the output amplitude. That is the easiest way to do this. And the way we did that was, we said that the current profile through the true transistors are going to be like this. They are basically square waves going from 0 to IT. When the transistor is off, the current is 0. Transistor is on, the current is IT. Okay? And the real equivalent circuit of the oscillator, of the cross coupled portion, is going to be this. Right? It is going to be a current source which is switching from minus IT to IT. Okay? And flowing into the RLC tank. What we did was, we took one half of this circuit, so that is going from 0 to IT, flowing through this RLC to give you this voltage V1. Okay? And in this specific case, we split up the Fourier series coefficients of the square wave. It obviously has a DC component equal to IT by 2. So this is actually 2 by pi. Sorry for the error. This is actually 2 by pi. Okay. So obviously the differential voltage will be 4 by pi. This will be the amplitude. The amplitude will be 2 by pi. Okay, on either side. Okay. Now, so we have analyzed the the differential cross-coupled oscillator. Now, if you look at the version we actually built, okay, we actually built this version. Some V bias to give you this current IT, right? This is probably what it's going to look like. You have a current source. Most probably that current source is going to be a transistor, right? With a bias voltage. Maybe a current mirror. Okay? Now, can you think of some variants to this circuit? Do I necessarily have to have an NMOS cross-coupled pair, or can I have a PMOS cross-coupled pair? I can have a PMOS cross-coupled pair also. Nothing wrong with that. It looks slightly different. So, I have this to give me IT. Okay, I have this. So the PMOS variant will look like this, right? I've just drawn the exact thing where only thing is I've placed the active portion with a PMOS. Is that all, or are there other variants? Actually, first of all, why would I be interested in the PMOS variant? What are the differences between circuit, let us say 1 and circuit 2? Common mode voltage, okay. Output common voltage is different, but that's very easy to write. Most probably if you take the output, you're going to do this on either case. Right? You're probably going to do that. So that is not a major problem. Swing. Okay. What is the swing difference in between 1 and 2? What is the swing in 1? So let us say this was RLC, and I take the exact same RLC. What is the swing in 1? 4 by 5 IT times R. What is the swing in the case of 2? Exactly the same, right? If you were to replace the PMOS cross-coupled para with an equivalent circuit, it will be exactly the same. That will also be a square wave, plus or minus IT. So this will also be 4 by pi IT times R. So what are the differences? Come on, think. What are the differences between NMOSs and PMOSs? Vinay, what differences can you think of between NMOS and PMOS? Yeah, so what is that mobility? How does that translate here? Yeah, mobility is the only difference, you're right. Right? Okay, so it will be faster, but are you interested in speed here in some fashion, or what are you interested in? So what will oscillate faster? Why? What do you mean by oscillate faster? Because the oscillation frequency is just 1 over root LC, right? The angular frequency is 1 over root LC. That does not change, or at least more or less is the same between the two. Correct? So what was the other one you said? It will start up faster. Why is that? Suppose I want to make the two circuits start up at the same speed. What would you do? Size what? You will make the PMOS larger, maybe by 2 to 3 times, depending on the mobility factor. Okay? If you size the PMOS, 2 to 3 times larger than the NMOS, you will get the same startup time. Correct? Okay, let us say I do that. No, we have not reached phase noise yet, right? So I am not even dealing with that. There is a difference in phase noise, but we are not dealing with that. Okay, so what will that give us? Okay, so that may be a definite advantage, because you have separate N wells, you can actually get rid of the body effect. Correct? For the PMOSs. Okay, so definitely that is the thing. Okay, let us go back to this thing, right? I am making the, let us say this was GMP and this was GMN, right? I am going to make this GMP equal to GMN. So can you think of what will happen when I try to do this? I am making the PMOS 2 to 3 times larger. What effect do you think it will have on some other characteristic of the oscillator? Yeah, parasitic cap, right? The minute you make the PMOS 3 times larger, it will have 3 times larger parasitic cap.
But that can be observed in the
Okay, so now he says that can be absorbed in this capacitance, right? You are right. However, there is one important characteristic of the oscillator that we have not talked about yet, which is the tuning range. If you remember, let us go back to the first lecture on oscillators. You remember this? This particular characteristic, right? What does this tell you? It tells you depending on how much you, depending on the values of obviously KVCO and VC, the range of VC, there is a certain F max and F min that you can achieve with any oscillator. Correct? There is a certain maximum frequency and minimum frequency that you can achieve with any oscillator. What do you think we are going to try to do when we design this oscillator? You are going to try to maximize F max by F min, right? Because you want to maximize the tuning range of any oscillator. Why would you want to do that? Can you imagine any reason why we would want to maximize the tuning range? Why do we want to maximize this tuning range?
It can be used for identity, like in super receiver, like to down convert the signal to different features.
Okay. So first of all, it needs to have some tuning range, right? I hope you agree with that. It cannot just be a fixed frequency oscillator for a number of reasons. Obviously, if you had a fixed frequency oscillator, it's not even possible to create a PLL to lock it to a fixed frequency. You are obviously, this fixed frequency is going to vary with temperature process and so on, right? So you need to have some tuning range, correct? Now, let us take the case of a super heterodyne receiver. Okay, let us look at the first LO. What frequency does the first LO have to be at? Come on guys. Huh? IF plus RF. Okay, IF plus RF. Is it fixed or varying? Is it varying always? That really depends on whether I choose a fixed IF or a sliding IF. I actually have the option of choosing a fixed oscillator and choose a sliding IF also. Right? Nobody said you shouldn't do that. If my intermediate frequency was 200 megahertz and my input RF varied maybe over a 50 megahertz band, maybe I can go from 175 to 225 for the IF and tune my IF components accordingly. Maybe my amplifier has enough bandwidth. The tough part actually comes in probably getting a filter to actually accommodate this varying IF. Right? So normally that is not a very popular choice. And it's a lot easier to create a varying LO compared to a sliding IF. Okay, so let us say IF was fixed. Then what happens? Then if my RF frequency is 50 megahertz, my LO also has to accommodate this 50 megahertz range. Correct? In fact, if LO was 50 megahertz, if my VCO was twice that frequency, and that is common, right? Twice and 4 times is common, then VCO, let us say if it is twice, the VCO frequency has to be 100 megahertz tuning range, not just 50 megahertz. Agree? Okay. Now let us take the case of, let's say a modern cell phone, right? Maybe I have a band from, let us say, I'll just give you approximate frequencies, maybe 800 to 850 megahertz. I have another band from 900 to 950 megahertz. Maybe I have other bands also, and there are other bands, right? But I have one band from 1800 to 1850, and I have another band from 1900 to 1950. Okay? I have these 4 bands. Are you going to have 4 PLLs? Obviously, it's crazy to have 4 PLLs, right? You need to find some other easy way to do this. Let us take the simplest example. Let us dump the higher bands also. Okay, let us take only the case of 850 to 900 and 800 to 850 and 900 to 950. Okay, how would you accommodate this with 1 PLL? Change the free running. No, change the free running frequency of the VCO. How do you change the free running? We have not even discussed what the free running frequency of the VCO is. Right? What is the free running frequency of the VCO? When the control voltage is 0. Really, that is of no particular significance for us, right? Does it have any particular significance for us? It does. It does. You are right. We do that. But I want to see if other people understand how we do that and why we do that. He said change the free running frequency of the VCO. Does that make sense to everybody, and why? Because that is a little bit more advanced from the point I was trying to make. So let us not consider that now. But that is obviously done in any modern oscillator. But let us not even consider that now. How would you accommodate an LO of 800 to 850 and 900 to 950?
So choose an LO which has a tuning range from 800 plus IF to 950 plus IF.
That's all, right? That is the most obvious solution, is to go from 800 plus IF to 950 plus IF. So what was earlier only a 50 megahertz has now become 150 megahertz. Suppose I had another band from 1000 to 1050, right? I would have to expand the tuning range of the VCO to actually cover that also. Now obviously what that means is the tuning range of the VCO is now obviously increasing. Obviously this is a percentage tuning range, right? This is a percentage tuning range, and you are obviously increasing this Fmax by Fmin requirement, right? How do you define Fmax by Fmin? Actually, what is Fmax and what is Fmin? Okay. So you have some specification. For the VCO, what is it? So let me do this. KVCO times VC plus the free running. This is the fundamental equation of the oscillator. Correct? This is the fundamental equation of the oscillator. What are the parameters that affect Fmax and Fmin? Let us assume that the free running frequency is constant. If you want very large Fmax by Fmin, first of all, what is Fmin? If your free running frequency is constant, what is Fmin? Come on, people. It is a free running frequency, right? Because actually, does it have to be always the case? If negative supplies are allowed, you can go lower. But right now we are assuming that you have only some 0 and VDD. Okay. What is the maximum frequency? FFR plus KVCO times the supply. Let us assume you can tune till the supply. Correct? So really, what defines the maximum frequency is the KVCO and the supply voltage. Supply voltage is fixed. So therefore it is just the KVCO. Okay, what is this KVCO? Change in the frequency with respect to voltage. So far, in all the oscillators we have seen, they are all fixed frequency oscillators. We have said omega naught is 1 over root LC. Right? Let's go back to our cross-coupled oscillator. Right? What is the frequency of oscillation? Omega naught is 1 over root LC. Correct? In this particular case, coming back to the point which I was trying to make, it is not just omega naught is 1 over root LC, because you know you have parasitic capacitance from the transistors. So the actual frequency is omega naught is 1 over root L times C plus Cp, where this is the parasitic cap. This parasitic cap could be coming from the transistors, could be coming from the inductor, maybe from the capacitor itself. Okay, even if you take a linear capacitor like this between nodes A and B, you will have some capacitance to ground from both sides. Okay, so all of these will have some parasitic capacitance. We'll have some parasitic capacitance from the inductor, parasitic capacitance from the transistors themselves. Correct? Now let us get back to our tuning range. How would you tune the oscillator? You need to get some way to change either the inductor or the capacitor as a function of voltage. Because the frequency is just 1 over root LC. Correct? Which is easier? Most probably the capacitor. Because the inductance does not vary as a function of voltage. It's not a very strong function of voltage at all. Right? Of a DC voltage. If you take the capacitance, of course you know cases where The capacitance is a function of the DC voltage. Classic example is what? A PN junction, a reverse bias PN junction. The depletion region width is a function of the voltage, and therefore the capacitance is a function of the voltage. Okay, so you are perfectly welcome to use a junction diode. Okay, a reverse bias junction diode can give you your voltage variable capacitance. Can you think of anything else that gives you voltage variable capacitance? MOS capacitor, right? Maybe something like this, let us say. Okay, something like this will also give you a voltage variable capacitance. Unfortunately, this kind of guide does not give you a monotonic voltage behavior. You'll have to do something different. Okay, but you can get voltage variable capacitances, even from MOSFETs. Why is that? Why does a MOSFET give you voltage variable capacitance? Varies? Why is that? So let us take the case of the inversion region. What is the capacitance? Depends on which nodes you are looking at. But let us consider this particular case where I am shorting together the the drain, source and bulk. Right? What is the capacitance in the inversion region? WL mu Cox. WL Cox. Why is it WL Cox? Correct. So you have inverted, and obviously the drain source bulk connection is connected to the inversion region. The other source, the other node of the capacitor is the gate. What do you have capacitance between them? WL Cox. Correct? So in inversion, WL Cox. Correct? If I keep reducing the voltage, obviously this will happen when the gate source voltage is very large, right? When the transistor is actually inverted. If I actually reduce it below Vt, what happens? Eventually, if I keep reducing it, the inversion region will not have formed, right? And I'll only have a depletion region. So I'll only have the depletion capacitance. Now in this particular case, if I actually decrease the voltage even further, you will have what is called accumulation, and you will again have a same WLC of capacitance, but definitely in a certain region you can go from some WLC ox, which is C max, okay, to C min, which is your depletion region, depletion capacitance, which is much smaller. Okay, depending on the various parameters of the MOSFET, this can be very large. Okay, anywhere from 2, 3 to maybe 10 or 11. Okay, it really depends on the parameters of the MOSFET. But the nice thing about it is possible to get voltage variable capacitors. Okay, what do we do next? We take this capacitor and stick it inside our oscillator. So the most the simplest version, we are going to replace this capacitance, this C capacitance, with that voltage variable capacitance. The minute we do that, the frequency of operation will vary from 1 over root L. So F max will be 1 over L into Cp plus C min. Okay. F min will be 1 over root L into Cp plus C max. Correct? Okay. Now, earlier I had assumed that C max by C min limits F max by F min, but that is not true, because you will have various parasitic capacitances Cp. So the actual C max by C min, okay, actual Cmax by Cmin will be, 1 minute, actual Cmax by Cmin will be Cp plus Cmax of device over Cp plus Cmin of device, whatever device you are using. Obviously, this will always be smaller than Cmax by Cmin of the device itself. Okay, this will always be smaller than the Cmax by Cmin of the device itself. So one of the consequences of using a PMOS oscillator, for example, a PMOS cross-coupled pair oscillator, for example, is the reduction in tuning range of the oscillator. Right? Okay. So did everybody understand this tuning range problem very well? Okay, so let us go back to these two variants. Are these the only two variants possible? Huh? Okay, we'll come to that. Anything else just for this particular case? Do I have to use let us say an NMOS current source here, or do I have to use a PMOS current source here? Of course not, right? I can actually choose to do this. So right? I can very well choose to take the NMOS cross-coupled pair oscillator and drive it with the PMOS current source. What is the difference between the two cases? Obviously, the output common mode is going to be different, right? That is a given. Anything else? Parasitics will increase. Why? PMOS parasitics will also come into account. What do you think? So he says that the PMOS parasitics will affect it. So maybe I'll just draw it as a separate cap here. Cp of the current source. Okay, what do you guys think? So let us see what that now. I also need to draw up the NMOS case. So I have drawn the PMOS cross-coupled pair. I have drawn the NMOS cross-coupled pair. Obviously the NMOS sources will be grounded. Where do I connect the tank? Obviously in this case it looks slightly different. I'm going to connect the tank like this. Okay, I no longer have a tank with the center connected to VDD. I now have a tank connected between these two nodes. Okay, so let us take the case, the first example. So he said that for the same current I get twice the negative resistance. Correct? So let us say this was GMN, and I make sure that this GMP equals GMN. Suppose I had taken the original NMOS cross-coupled oscillator and just made the GM 4 times. Would I still have got this twice the GM? Made the width 4 times for the same current. Would I still have got twice the GM? I am using the same current IT. Obviously, I am going to keep power consumption the same. Correct? I am going to compare this with the original case, except I am making the width 4 times, so that the GMN is twice. I don't have any GMP in that case. I am going to compare the two cases. Current consumption is the same. Agreed. What is the overall negative resistance? What is the overall negative resistance in this case? Minus 2 by GMN plus GMP. Okay. So in this particular case, it will be minus 1 over GMN. Remember, a smaller negative resistance is stronger. Right? In the other case, I will again get minus 2 over 2 GMN. That will also give you minus 1 over GMN. So what is the advantage of this case? What about the parasitic capacitance? To get GMP equal to GMN, I'll probably have to make the PMOS 3 times. So the parasitic capacitance of this in this case is going to be, if this had CP, okay, maybe this has 3 CP, okay. If I assume, look only at the transistors, I have 4 times the parasitic capacitance. In the original case, how much did I have? So let me draw that also. I have some V bias. Okay, I have said that I am going to make this 4 times the width so that I get twice the GM. Correct? What is minus RA? Minus 2 over GMN is minus 1 over GMN. LC, LC. Same current consumption. What is CP? 4 times. So what's the difference? Why would I even go with an NMOS? Why not just take the same original, NMOS cross-coupled oscillator and just, make the NMOS device size 4 times. So really current reuse is not a real advantage, obviously, right? I have the same parasitic capacitance, same negative resistance. Those are the 2 parameters we have looked at for the oscillator. Right? What have we looked at? We have looked at current consumption. It is obviously VDD times IT, power consumption. That is the same in both cases. Tuning range is defined by the parasitic capacitance. That is also the same in both cases. So what could be the difference? What else have we seen? What other characteristic of the oscillator have we seen that could be different, which we'll have to analyze in more detail? Save area. Why is that? Very good point. You have only one inductor in that case. Here he says you have two inductors. Okay. Suppose I make this a center tap inductor. I make it a single inductor with a center tap. Right? Really it's a symmetric circuit. So, but that's an important point you bring up. So what I'm going to say is, I'm going to redraw the circuit slightly differently in the NMOS case. Okay. I'm going to draw it as a single circuit and then I'm going to connect my cross-coupled pair here. That is very easily done, right? A center tap inductor will occupy not much more area, but now there is a difference. The inductance of the center tap is 2L. Right? What is the capacitance? The way I have drawn it, it has to be C by 2, and this resistance has to be 2R. Correct? That is because I actually took LC and RLC on either side. I didn't consider it as a center tap. But suppose I do consider it as a center tap, I need to use twice the inductance. It is going to use twice the area. What is one easy way of handling this? That's very easy, right? All I will do is, I'll take this guy, I'll use an inductance of L, I'll use a capacitance of C. Obviously the resistance will also come down, okay, to R. And now I have normalized the area also. What else is left? Why? Oh, but now let us say I compare it with this particular case. Okay, let us say you're right, the conditions were different because I was using a center tap inductor in one case, I was using two RLC tanks. We said we can make it a single RLC tank using a center tap inductor. And then I also said you can normalize it back to the same value of inductance also, because really the frequency of operation depends on 1 over root L times C. If I increase C, I can cut down L and get the same oscillation frequency. What else is the problem? Okay, good question. What will an inductor look like? So, I have an inductor like this. Can I exactly locate the center? Of course I can, right? Why can't I? The center is exactly located halfway down. I mean, these are all things you are drawing, right? You are going to draw the inductor. You take the same length of metal and put it right in the, it's very easy to draw a symmetric structure. Okay? Because you have control over exactly what you are drawing. The resolution of these drawings is very, very low. Okay? So the resolution of these, to give you an example, the size of these inductors, the diameters, maybe a couple of hundred microns. The resolution of your drawing is going to be 0.1 or 0.01 microns. Actually, it will be 0.01 microns in some of the latest technology. Okay? You can get as close to symmetric as possible. In other words, what I am saying is, I am going to compare this. In the case of the NMOS, I am going to use this. It has an inductance L. In the case of the NMOS PMOS, I am going to use exactly the same thing. Okay? Without this guy. That is all I am saying. Right? And at the end of the day, the center tap is actually, since you're driving it differentially, anything connected on the center tap doesn't matter. So what is the other characteristic of the oscillator that we have figured out so far? Why don't you go back through your notes and check. What all have we looked at? We looked at the startup condition, we looked at the negative resistance, we looked at condition for stable oscillations. Today we did Cmax, parasitic capacitance, Cmax, Siemens and so on. What else? Come on people. There's a really important characteristic we just did. Right? There's an important characteristic we just derived at the end of last class. Just note the error, okay? It is actually V1 should be IT times 2 by pi times R, not 1 by pi times R. That was a small error in last class. Okay? But output amplitude was an important characteristic that we actually defined. So now we need to see if these two oscillators are different in terms of output amplitude. Now let us take a step back. Let us go back to this NMOS oscillator. So I have normalized the inductance value, RLC. What should the output amplitude be? In the earlier case, we had 4 by pi times IT times R, but now it will be 2 by pi times IT times R. Okay? With the normalized RLC tank. And that really is the right way to compare two circuits. Because obviously if I can double the inductance for the same Q, I can actually, for the same set of losses, I will get double the resistance probably. Right? So that is not the right way of, if you can't have different values of inductances and try to compare it. Okay? Now I need to find out what the output amplitude of the complementary NMOS PMOS oscillator is. The NMOS PMOS oscillator is also called the complementary oscillator. So this is complementary cross-coupled VCO. It's called complementary obviously because you have both NMOS and PMOS. Okay, so I want you to think about this. We'll continue next class.